Hi everyone! Today we are going to do the Millikan oil experiment together in a video. This experiment consists in determining the electric charge carried by a particle by measuring the force experienced by the particle in an electric field of known strength. It is fairly easy to produce a non-electric field, however, detecting the tiny force on the particle isn't so trivial. Measuring these tiny forces is the reason for the success of the Millikan oils experiment. For that, we will observe the velocity of fall of small charged oil droplets. Before we go to the experiment, let me introduce you the equations that rule the data analysis in this experiment. I know it can be terrifying at first, but bear with me. In the end, it will be beautiful. Let's start with our happy little oil droplet in a free fall. When this droplet reached its terminal velocity, which effectively happens in a matter of milliseconds in our experiment, the net forces acting are zero. Therefore, the velocity of fall, Vf, times the coefficient of friction between the air and the drop, k, will be equal to the mass of the drop, m, times the acceleration of gravity. The situation, of course, changes when there is an electric field. In this case, the drop is rising and the forces, when we balance the forces, we get to equation 2, where E is the electric intensity, Q is the charge carried by the drop, and VR is the velocity of rise. In both cases, there is some air resistance, but we can consider it insignificant. From equation 1 and 2, we can solve it for Q, giving us equation 3. To remove the mass on our equation 3, we can use density relation. Since density is mass over volume, the mass can be substituted by the volume of the sphere of the droplet times the density of the oil. In here, A is the radius of the droplet and ρ is the density of the oil. Substituting 4 to 3, we get our new equation 5. Now you might think, how to determine the radius of the droplet? Well, that's a very good question. For that, we can use the Stokes law, which relates the radius A of a spherical body to its velocity of fall Vf in a viscous medium, with the coefficient of viscosity eta. I wrote the Stokes law at the bottom of the slide, and if we set the formula for Stokes law equal to the right-hand term in the equation 4 highlighted in yellow, we can solve it for A and get to equation 6. Unfortunately, due to the small velocity of our droplets, we need to correct this oil viscosity in Stokes law. The viscosity we should use is called effective viscosity, and its value is effectively multiplied by the viscosity. This is equation 7. It depends on a constant P, the atmospheric pressure P, and the radius of the droplet A. Now we can substitute the viscosity in equation 6 to the effective viscosity in equation 7 and get to the equation 8. We can then manipulate equation 8 to remove the term A from inside the square root, obtaining equation 9. Now we can come back to equation 5, finally. We are almost there, believe me. We then substitute equation 9 in equation 5. Since the electric intensity E equals the potential difference across the plates V over the separation of the plates in the droplet viewing chamber D, we can get to our final equation 11 by removing E from 10. And 11 is the equation we are going to use to calculate for the calculation of the charge. Now we can go for the experiment. In here, I'm showing you more or less the necessary equipment for this proc. We're using the Millikan oil apparatus from Pasco. We need the atomizer, a mineral oil, a power supply, a multimeter, a rod stand, and something to measure the spacer. The components of the droplet viewing chamber are a lid, clear plastic chamber cover, housing, convex lens, not showing in here, droplet hole cover, the upper capacitor plate made out of brass, a plastic spacer, the lower capacitor plate, also a brass one, an alpha source, and an electrical connection to the upper capacitor plate. The first step of this experiment is to deassemble the droplet viewing chamber by lifting the housing and then removing the upper capacitor plate and the spacer plate. As you can see, David is actually cleaning everything, and this is super important for this practice so we can get good results out of it. We then are looking to measuring the thickness of the spacer plate. The thickness is our D in the equation. Then we should align the optical system by reassembling the plastic spacer and the upper capacitor plate onto the lower capacitor plate. Now we can see where we can get the focusing wire. The next step is to insert the focusing wire into the hole in the center of the upper capacitor plate. We can then bring the reticle into focus by turning the reticle focusing ring on the viewing scope. We can view the focusing wire through the viewing scope and bring the wire into sharp focus by turning the droplet focusing ring. With everything in place, we can turn on the high voltage. In this case, we used 500 volts DC. One of the parameters in our equation is the air viscosity. The way to determine it is by knowing the temperature inside the chamber. We should determine it by connecting the multimeter to the thermistor connectors on the platform in order to measure the resistance of the thermistor that is embedded in the lower capacitor plate. This temperature should be checked frequently. Once with the temperature, we can easily relate it to the air viscosity by the graph shown in here. Now we can do the experiment using the atomizer. First, we prepare the atomizer by rapidly squeezing the bulb until oil is spraying out. Then, we move the ionization source lever to the spray droplet position to allow air to escape from the chamber during the introduction of droplets into the chamber. We place the tip of the atomizer into the hole on the lid of the droplet viewing chamber, and while observing through the viewing scope, squeeze the atomizer bulb with one quick squeeze. When a shower of drops can be seen through the viewing scope, we move the ionization source lever to the off position. We should then charge the plates positive or negatively, as we wish, and as many times as we want, until we get enough droplets in the appropriate speed. In here, we recorded the viewing scope, and that's what you're seeing now. To determine the electric charge, we need to select appropriate droplets. It is not a very easy task, and it requires a certain skill level to obtain a good spray to begin with. Ideally, we should select droplets which rise and fall slowly, indicating that those droplets have a small number of excess electrons. Then, we should observe several droplets. After doing the math, we expect to obtain a charge that is integral multiples of a certain smallest charge. If we succeed, that is a good indication of the atomic nature of electricity. And that's it. Now you know how one of the most iconic physics experiments is performed. I hope you have enjoyed. See you next time!